Hello, welcome to this first episode of a series of videos where we build a virtual machine in Haskell. So I was thinking about this project some time back, and then I thought it's a good idea to do this live. Just code it from scratch, build it from scratch. So you can see the home page on the screen. Um, the links are given in the description. Feel free to clone this. And before we get started, a few things about this project. The goal for me in this project is just to have some fun. It's a hobby project, of course. My aim is not to build a production ready virtual machine. And since we are building this from scratch, this is going to take a number of episodes. It's not a small project. All the videos will be recorded. You can watch them in the channel. So what is this project all about? Let's start from there and then get started with it. The idea is to build a virtual machine which is an abstract computer. So if you go to this link, the home page of the project, there is a specification here which is very detailed. It talks about what kind of a computer is this. By the way, the name of the project is Pixie, as you can see here. So this explains the architecture of Pixie, how it works in detail. There are a whole bunch of details about its operation, its mode of operation, what kind of memory does it work on, the registers and so on. But for now, just to get started, I am not going to go into all the details. We will revisit a lot of these as we start building this. So let's get started with the most important details, and then slowly, as we start building each of these components in this project, we will look at some of these things in detail. We will come back and revisit some of this. But in case you want to take a look at this offline, of course, as I mentioned, the details are available in the description. So you can follow the link and then read through this document. So what is this project all about? It's about building this virtual machine named Pixie, and its architecture is very similar to most of the conventional CPUs. This is a register-based CPU. So there are 32 general purpose registers named R0 to R31, and they are 32-bit wide. So each register can hold a 32-bit number. You can use each of these registers for any purpose. There is one register which is special. We will see that in a moment. R15, the 16th register, is a little bit special. It's used as a stack pointer. So some instructions will treat this register in a special way. But other than that, any register, anything from R0 to R31, you can use it for almost all the instructions. There is nothing special about them. And one more thing I should point out is that this is a RISC CPU, reduced instruction set computer, or in another way of saying that would be, this is a load store architecture computer, in the sense all the instructions, or almost all the instructions, will operate on the registers. You cannot have an operand. So let's say you're adding two numbers, both the input numbers and the output, all of them should be in registers. You cannot have some operation directly in memory. So you first load, if your operand is in memory, you first load that into a register, perform some operations, and then write it back into memory. So there is a load and store operation involved in this. That's what it means. So now, other than these general purpose registers, since we mentioned memory already, the memory address space for Pixie is 1 MB. So the addresses are 20-bit. They go from address 0 to FFFFF in hexadecimal. And each memory location, each memory address stores 1 byte. So that will come to 1 MB if you do the math. Now, in addition to the general purpose registers, there are some special registers. The first one is the program counter, which is at 20-bit because it stores an address, right? So it is a 20-bit register. It stores an address, and this address is the memory location, is the address of the memory location in which the next instruction to be executed will be found. So the CPU will look at the program counter register to figure out the address of the next instruction to be fetched. So it will fetch that instruction and then execute it. And then it will increase the program counter to point to a new instruction, then fetch that and execute. And this keeps happening, and this continues in a loop. That's how the CPU operates. The second special register is called machine status register. This is a 32-bit register. In the current version of Pixie, only 4 bits are used. All other bits are undefined. Bits 0, 1, and 2 are used to represent a 0 flag, a positive flag, or a negative flag. So the intention is that once you perform some sort of operation, or arithmetic operation or a logical operation, depending on the result of the operation, if the result is a 0 value, then the 0 flag will be set. If it is a positive value, the positive flag will be set. And if it is a negative value, the negative flag will be set. So you can have instructions. We haven't looked at the instructions yet, but once we look at the instruction, this will be very clear. There are instructions which look at the value of these flags, and then depending on the value of the flag, you can do certain things. So for example, if you implement a conditional operation in any programming language, this is how you do this. You do an addition or a subtraction or a comparison, and then depending on the result, either the 0 flag or a positive flag or negative flag will be set. And then based on that, you do something else. That's the idea. There is one more bit, the bit number 16, which is called the mode indicator bit. This is very important because the CPU can operate in 2 different modes. There is a user mode and a supervisor mode. The user mode is when you have the regular user programs running. When you write a program for the CPU and then execute it, the CPU will be in user mode. But the operating system or device drivers, they do not operate in user mode. They operate in a special mode called the supervisor mode. So when the CPU is executing in supervisor mode, this mode indicator bit will be set. And why is that important? That is important because certain operations are allowed only in the supervisor mode. So for example, if you want to access some input-output devices, which we will see in a moment, it's possible only if the CPU is in the supervisor mode. User programs cannot directly access devices connected to this computer. Okay, so we will see the details about this in a moment, but before that, let's look at one last register. This is called the supervisor stack pointer register. So again, like I mentioned, there are two modes. There is a user mode and supervisor mode. And there are certain scenarios in which we will switch the computer, the CPU, from user mode into supervisor mode. When we do that, we need a special area in memory called stack. Like I said, the register R15 is a stack pointer, and stack is generally used to hold either your local variables of a procedure that you're executing, a subroutine that you're executing, or to hold other information like return address of the calling subroutine and many other things. So now when you switch to the supervisor mode, we do not want to use the same stack that the program was using, the user mode program was using. We want a separate stack so that we know exactly how big it is, we know how much data we can store and so on. The operating system shouldn't depend on the user program setting up a good stack. It may not set up anything. We don't know that. So just to make the operating system a bit more robust, there is this register called supervisor stack pointer register, which is used once the CPU switches to the supervisor mode. And we will see how all these are used in a moment. Now, finally, there is also an I/O address space. This is input-output address space separate from the memory address space. Now, some of the CPUs might be, you might be familiar with, might be using a memory mapped device model. It's possible that the input-output devices are mapped to some area in memory, and then you access those memory locations to read and write data from or to these input-output devices. On the other hand, Pixie has a different architecture. It has an separate I/O address space, and each of the I/O devices connected to these address spaces can be accessed through I/O ports, one or more input-output ports. There are 256 distinct input-output ports, and each of those ports are 32-bit wide. So every time you read or write, you are dealing with a word which is of 32 bits in size. Okay, so this is the overall high-level architecture. Now we will look at some of the details. Like I mentioned before, we are not going into all the details, which it's too much detail at this point. I think we should just get started with bare minimum possible. And then once we start building some of the components, then we can revisit some of these areas. And in case you have questions, feel free to post them in the chat. I'll try to answer. So I mentioned that the input-output port and the registers are 32-bit, but then Pixie can deal with a bunch of different data types. It's not just 32 bits. So it supports operations on bytes, which are 8 bits, and shorts, which are 16-bit, words 32 bits, and there are some scenarios where it will operate on 64 bits. If I remember correctly, this is just one instruction, but there is a case where it will operate on 64-bit double words as well. And it is a little endian machine, which means if you have a byte, the lowest bit stores the least significant value, least significant bit. Similarly, if you have a short or a word or double word, they are going to occupy multiple bytes in memory. So let's say it's a short. So there are 2 bytes, and the lowest address will store the least significant byte, and the high address, the immediate next byte, will be the most significant byte, and so on. So this is a little endian machine, and an additional restriction is that all the memory accesses must be naturally aligned, which means if you have a short, it has to start at an even memory address. It has to be divisible by 2. Words should be located at an address which is divisible by 4, and double words must be located at an address divisible by 8. It's an error if any operation tried to access an unaligned memory address. So for example, if you have an odd address and you are trying to access a short or a word or double word, it will encounter some sort of error. And we will see what kind of error it is, but at this point, it's good enough to know that this will run into some error. So now let's look at some of these special registers, how they are used and so on. One obvious place where we need this is when the user program makes a system call. So you have a program running and then it requires some service from the operating system. The way to do this in Pixie is to make a system call. So there is a special instruction called system call instruction, and you make a system call by specifying a system call number. So there are 64 distinct system calls possible in Pixie. So the operating system can have 64 separate system calls enabled at a point in time. Of course, it can have less than that, but maximum possible is 64 distinct system calls. So once a system call instruction is executed, that instruction will have the number of the system call in it. Once that is done, the CPU performs a number of steps. The first thing it does is there is an area in memory called system call table, which holds, it's an array. It holds 64 elements, and each element has 2 parts. There is an enabled or disabled flag, and there is also an address of a handler to handle the system call. So the enabled or disabled flag will tell us whether this particular specific system call is enabled. So let's say the program makes a call to system call number 10. The CPU will consult the system call table. It will look at the 10th entry in the table, and it will check if this is enabled or disabled. If it is disabled, then it's an error. If it is enabled, the CPU continues with some more things. The first thing it does is, like I mentioned before, it has to set up a new stack. So it will switch to a new supervisor stack by reading the value of the supervisor stack pointer register and store it into R15. Remember, R15 is the stack pointer. So it will save the value from supervisor stack pointer register into R15. So now it has switched to the new stack. And in this new stack, first it will save the old value of R15 so that it's not lost. The idea is once we process this system call, we can restore this saved value later. And it will also store the machine status register and the program counter register into this stack. Again, the idea is once we've complete the system call, we can restore all these values. So remember, the machine status register holds all these flags which we don't want to lose, and program counter contains the address of the next instruction to be executed after the system call. So it will we obviously want to preserve that as well. So once these are saved into this new stack, the next thing to do is, if you remember, the machine status register has this mode indicator flag. It will set that flag to indicate now the CPU is switching to the supervisor mode. And now it has to execute this system called handler. The address of the handler is there in the system call table. The CPU takes that handler address, puts it into program counter, and now it's ready to execute the system call. Any parameters to be passed from the user program to the system call, all those are passed in other general purpose registers. So that's not an issue, right? All the registers are preserved. So now the handler can look at these registers, figure out what to do, perform any operations required. And when it is ready to return, there is a special instruction which we will see when we start looking at the instructions. That instruction will restore all these values saved, the program counter, the old machine status, and the old value of R15 back into the respective places. And now the CPU will just go back to the user mode program. And again, any return value from the system call will be passed back in the general purpose registers, R0 to R31 except R15, which is a stack pointer. So this is how a system call from a program, user program, to the operating system is made. Now, similarly, there is also another special scenario in which we should switch from one mode to another. This is called interrupt handling. Interrupts are sort of asynchronous events raised by an input or output device. So let's say there is a keyboard connected to your computer and you press a key. The keyboard raises an asynchronous event. It is asynchronous because we don't know when the user is going to press the key. So it raises this event called, or raises an interrupt. And again, each device can raise different interrupts. So there are multiple possible interrupts. There are 64 interrupts possible in Pixie. So each interrupt has a number associated with it, which is called interrupt vector. So the interrupt comes in and the CPU will detect that there is a pending interrupt to be serviced. And what it does at that point is it will pause whatever is getting executed. It will save the current state and then execute a special handler. This is very, very similar to the system call handling that we saw earlier. So it will save this state and then switch to a handler to handle this interrupt. And then once that is finished, it will return back to whatever it was executing previously. So you look at the steps it is going to perform, it's very similar. There is this special area in memory called interrupt vector table, very similar to system call table. And that holds 64 possible entries for each interrupt vector. So depending on the interrupt vector, it will pick the correct entry from this interrupt vector table, check whether it is enabled. If it is disabled, it is an error. And then if it is enabled, again, it will first switch to the supervisor mode stack. And just similar to the system call handling, the supervisor stack pointer register is written to R15. And in this new stack, it will save the old R15, the old machine status register, old program counter, and now it is ready to execute the handler. So again, the mode indicator bit in the machine status register will be set to switch to the supervisor mode and then take the handler address and start executing that. And when it is ready to return, then the CPU will automatically restore all these old values from the stack and then just continue executing whatever it was executing previously. Now, where are these things stored? We talked about the interrupt vector table, system call table, operating system, user programs, all these things. They are stored in specific areas in memory. So the first 256 bytes for the 64 interrupt vectors. So each entry in the interrupt vector table is 4 bytes. It's one word. So 256 bytes in addresses 0 to FF is interrupt vector table. The next 256 is the system call table. And from that point onwards till hexadecimal 7FFF is the operating system. And hex 8000 and above is where the user programs will be loaded. So any address below hex 8000 is protected. If a user program tried to access any address below 8000, that will result in an error. Only the operating system or let's say a handler for an interrupt, all of them are privileged. They can access. So you know that these are privileged because when they execute at that time, the mode indicator bit will be set. So depending on that, the CPU will realize that this right now the CPU is in a privileged mode, in a supervisor mode, and access to memory below hexadecimal 8000 is allowed. If the mode indicator bit is clear and any instruction which is trying to access a memory location below hex 8000, it will result in some error. So this is the memory layout. And finally, when the CPU starts up, the registers and memory and various things that we discussed so far, they are all initialized to some specific states. So for example, all the general purpose registers are set with a value 0. The program counter is set to hexadecimal 200. And if you look at the previous slide, you can see that that is the first byte of the operating system. So that is supposed to have an instruction which is the entry point of the operating system. And then the machine status register will be set with just 2 bits. So the 0 flag will be set and the mode indicator flag also will be set, because when the CPU starts up, it's going to execute the operating system. So mode indicator should be set. The supervisor stack pointer is set to 0 when the CPU gets initialized. It's the job of the operating system to set up a supervisor mode stack and then fill the supervisor stack pointer register correctly. Similarly, all the interrupt vector table and system call table, all of them are set with 0 because 0 indicates they are not enabled. So if you remember, it had 2 parts. The word stored in each location of the IVT and SCT. It had an enable disable flag and it had an address. Setting this to 0 will ensure that the address is 0 and each of the entries are disabled. So any of the interrupts or any of the interrupts will not be processed, and any of the system calls result in an error. Again, the operating system is supposed to fill the correct entries into these interrupt vector table and system call table. The rest of the memory is not really initialized. So again, at this point, we haven't really seen how we will write a program, how is the operating system written. All those details are not defined yet. We have to figure out all these details. But till then, we can assume that the rest of the memory is not defined, at least by the specification. Okay, so this, I believe, was a good enough introduction to what we are trying to build. Now, what is involved in building this computer? What do we need to do? Obviously, if you look at the specification, there are few sections. So far, what I covered is mostly this section 2 about instruction set architecture. Some details are missing, but then that we will see later. The actual instructions that the CPU can execute are listed in section 3. And then there are some standard input-output devices which is explained in section 4. We will look at section 4 later. But if you go to 3, the instructions, so let's pick an example. So the first instruction is add. This will add two source operands and store the result in a destination operand. And there are two possible ways in which you can write this instruction. One is add a destination register DR, source register 1 and source register 2. So it will add source register 1 and 2 and then store the result into destination register. You can see the operation explained in pseudocode here, how this is going to execute. You can see there is a condition here if instruction 16 is equal to 0. That is because the instruction has two possible forms. One is the form that we saw already, where it is operating on 3 registers. It's also possible that we have one value in a register and the second value is a fixed value, or it's called an immediate value in the instruction itself. So for example, we could say add 32, the value 32 to register number 23 and store the result in register number 7. So that will be add R7 because that's the target. SR1 will be register 23 and then immediate value will be 32. So depending on whether we have an immediate value or a register as the operand, we will either do this operation where we add 2 registers, or we will take the immediate value. So here you should note that the immediate value is a 16-bit value. We will make it a 32-bit value and we will see how that is done. But extend the 16-bit value into 32-bit value, add it with the 32-bit value in SR1 and save it into the destination register. And then depending on the value that we calculated, set the 0 flag or positive flag or negative flag. That is the set flag. So this is the operation. So this is one instruction. Similarly, there are a bunch of instructions below. All of them are described in detail. Now, how do we implement this? If I want to build this computer, of course, I want to write programs for this computer. How will that work? How do I write, if I write a program like add R7, R23, R31, how do I generate the machine code? The machine code for this instruction is shown here. So if I have an instruction like this, it's represented this way in the machine code, and we will see this once we start building it. But how do I do this? So we need an assembler to take this symbolic instruction and convert that into machine language of this computer. So the first thing that we are going to build in this project is build an assembler for Pixie. Then once we have the assembler, we also need a virtual machine to execute those instructions. So that's the second part. So we will build, as a second part, we will build a virtual machine. Along with that, just having a virtual machine is not enough. You already saw that we need interrupt handlers, we need an operating system and so on. So we need some sort of system software. So we will write an operating system and system software, etc. Using the assembler that we already built. And we will figure out how to load this operating system into this computer. And if I write a user mode program, I should be able to load that also into this computer and execute it and so on. So all these things we will build one by one. Today, I don't plan to cover that. Today we'll stop at this point. In the next episode, when I come back, maybe we'll start building the assembler. We'll start building an assembler from scratch, which will accept instruction like what you're seeing here. Add dr sr1 sr2 and then convert it into a machine language code like what is given in this table. So that will be the first component that we are going to code. So that's all for today. In case you have questions, suggestions, please feel free to comment. I look forward to meeting you again. Thank you.